Now next is applications of the first isomorphism theorem. Note: if phi mapping from group G to group G bar is a group homomorphism, then kernel phi is a normal subgroup of G, and if N is a normal subgroup of G, then N is a kernel of some homomorphism on G. Let N be a normal subgroup of G. Define a map phi mapping from G to G by N as phi G is equals to Gn. Then phi is a homomorphism and how it is a homomorphism, because operation is preserved. Let G comma H belongs to domain G, phi GH. This is equal to GHN. Then by the property of coset, it can be written as Gn into Hn. By definition of phi, it will become phi G into phi H. And kernel phi is, we will pick an element of domain and it will be mapped to the identity of codomain, and identity of this quotient group is N. G belongs to G such that phi G, definition of phi is Gn equal to N. G belongs to G such that, again by property of coset, G belongs to N. So this is equal to N. Kernel phi is N. Now next, some important questions. How to find the number of group homomorphisms from S3 to Z6. So step 1 is write the subgroups of S3. So subgroups of S3 are H1 identity, H2 identity with 1 2, H3 identity with 1 3, H4 identity with 2 3, H4 identity with 1 2 3 1 3 2, and this was H5, and H6 is complete S3. Step 2, find the normal subgroups of S3. So firstly, what is the definition of normal subgroup? Do you remember?
The center of a group is equal to group. Normal XD XD X inverse belong to group. ऐसे कुछ था ना? Normal groups
Yes,
नहीं आता.
If G belongs to group G and H is a subgroup of G, then
The G and G inverse belong to the group. Yes.
belongs to H.
ठीक है.
So normal subgroups here will be H1 identity, H5 identity, 1, 2, 3, 1, 3, 2, and H6, S3. Basically, if I see this group, if I want to see whether it is normal or not, I will take this 1, 2, 3. 1, 2, 3 belongs to H5 and an element from group G also. Suppose I am taking this. So GH, G inverse 1, 2, 1, 2, 3. And what will be the inverse of 1, 2? Inverse बताया था मैंने. वन टू का इनवर्स 2, 1.
2, 1 हाँ वही.
Okay. So this is as it is. या फिर इकट्ठा ही कर देते हैं सभी का. Here 1 goes to 2, 2 goes to 3 and 3 goes to 3. Here 3 goes to 3, 3 goes to 1 and 1 goes to 2. Here 2 goes to 1, 1 goes to 2 and 2 goes to 1. इस पे वापस आ गया. So 1, 3, 2. This belongs to H5 ना. Similarly, I can see this element also. So these three are normal subgroups. Every normal subgroup can be a kernel of some possible homomorphism. Step 3. This is the important step. If H1 is equals to identity is the kernel of some homomorphism, then by first isomorphism theorem, what was first isomorphism theorem? G by kernel phi is isomorphic to image of G. So S3 by identity is isomorphic to image of S3. Now image of S3 will be a subgroup of Z6 and order of S3 by identity, it is 6, and order of image of S3 will also be 6, because we are taking that this is isomorphic to this. So now I need to check subgroup of Z6 of order 6. It will be Z6 itself. This implies that S3 upon identity is isomorphic to Z6, and we know that Zn is cyclic. So as Zn is cyclic, this implies that S3 by identity is cyclic, and we know that every cyclic group is abelian. This means that S3 is abelian, which is a contradiction. Can you tell me what is a contradiction here?
132 is not equal to 123, no?
Because S3 is non-abelian. Because S3 is a non-abelian group. Thus, identity cannot be a kernel of any homomorphism. So I have checked for this H1 equal to identity. Next I will check for this H5. If H5 is equals to identity, 1 2 3 1 3 2 is the kernel for any homomorphism from say phi mapping from S3 to Z6, then by first isomorphism theorem, S3 by H3, this will be isomorphic to phi of S3. Now what will be the order of S3 by H3? This will be simply order of S3 upon order of H3. Order of S3 is 3 factorial 6 upon order of H3 3. So this is 2. So order of phi S3 is also 2. Now as phi S3 is a subgroup of Z6 of order 2. Now number of elements of order 2 in Z6, ये देखना पड़ेगा अब हमें. Z6 क्या होता है? 0 1 2
3 4 5.
Number of elements of order 2, 0
3 होगा एक तो.
yes,
0 तो 1 3 होगा.
इसका 2 होगा, इसका 3, इसका तो 6 ही होगा.
6 होगा. इसका 3 होगा.
3
और इसका होगा 6.
yes, so only one element of order 2.
Hmm.
Thus there exists a homomorphism in this case. Means जिसके आइसोमॉर्फिक मैं कह रही हूँ ना कि अगर इसके पास ऑर्डर 2 का हमारे पास आ रहा है, इसका ऑर्डर 2 है ना, तो जिसके आइसोमॉर्फिक कह रही हूँ ना उसके पास उसी ऑर्डर का एलिमेंट होना चाहिए. यहाँ पे हमें मिल रहा है ना एक एलिमेंट, तो होमोमॉर्फिज्म एग्जिस्ट कर रहा है इनके बीच में. यहाँ पे हमारे पास कुछ ना कुछ कॉन्ट्रडिक्शन आ गई थी कि S3 एबिलियन आ गया था, तो इस वजह से H1 इक्वल टू जो आइडेंटिटी है वो आपका कर्नल नहीं है यहाँ पे. ठीक है. Now next, if H6 is equals to S3, so whenever our normal subgroup is equal to group itself, then it will always give a homomorphism, and that too a trivial one. This case always gives the trivial homomorphism as order of S3 upon H3. H6 हो गया ना, तो ये बना गया आपका. And if I want to check number of elements of order 1 in Z6, then I am getting one element of order 1 in Z6. So total number of homomorphism will be 2.
Just a minute.
One for H6 equal to S3 and one for H5.
Yes, 2.
Total 2 homomorphisms. Next question. Find the number of group homomorphisms from A4 to Z2. So this simply means A4 upon kernel phi is isomorphic to image phi, and image phi is a subgroup of Z2. So firstly, what are the normal subgroups of A4? There are 3 normal subgroups of A4. Identity, K4, clean spore group, and A4. So when kernel phi is identity, so A4 by identity. What is the order of A4? 4 factorial by 2?
Yes.
12. Is it possible for Z2 to have a subgroup of order 12?
No.
So this case is not possible. ऊपर मैंने डिटेल में करके दिखाया था, अब मैं शॉर्ट में लिख रही हूँ. सिर्फ नॉर्मल सबग्रुप देखने A4 के, फिर कर्नल देखना है कि कौन सा पॉसिबल है. अकॉर्डिंगली फिर हमें नंबर ऑफ ग्रुप होमोमॉर्फिज्म मिल जाएंगे. पेपर में भी ये शॉर्टली करना है, इतना सारा थोड़ी लिख सकते हैं. नेक्स्ट, इफ इट इज K4.
पेपर में आता है इसका क्वेश्चन ऐसा?
आता है.
अच्छा.
So K4, order of A4 by K4. So order of A4 is 12 upon order of K4, it is 4. So 3. Again, it is not possible for Z2 to have a subgroup of order 3. So this is also cancelled. Last is kernel phi equal to A4. In this case, we will have a trivial homomorphism. Trivial homomorphism. So there is only one homomorphism between A4 and Z2. Next, let G be a group with the generators A and B given by G equal to A comma B such that A to the power 4 is equals to B square equal to 1, BA is equals to A inverse B. If ZG denotes the center of G, then G by ZG is isomorphic to A part, the trivial group, B part, C2, the cyclic group of order 2, C part, C2 cross C2, D part, C4. Try this.
इसमें इसको नहीं बोलेंगे क्योंकि इनका ऑर्डर जो है एलिमेंट का ग्रुप में वो 4 और 2 है ना। बी का इस ऑर्डर 2 है और इनका ऑर्डर 4 है। तो अगर हम ये कहेंगे कि अगर जैसे ग्रुप में हमें एक एलिमेंट ऐसा होना चाहिए जो मिल जाए, तो जैसे C2 है द साइक्लिक ग्रुप ऑफ ऑर्डर 2, तो उससे आइसोमॉर्फिक होगा। तो बी ऑप्शन आना चाहिए एक तरीके से।
नहीं,
ये MCQ है ना ये।
MCQ है।
और या
पहले
फिर
पहले ये जज करो कि ये ग्रुप जी है क्या।
अच्छा, तो आयोटा नहीं, आयोटा तो नहीं हुआ ये। I4 इक्वल टू 1 होता है ना, तो I2 -1 होगा। तो 1 और -1
नहीं, डायहेड्रल ग्रुप नहीं है।
अच्छा, गॉट इट। रोटेशन और रिफ्लेक्शन।
डायहेड्रल ग्रुप ऑफ ऑर्डर 8। सो डायहेड्रल ग्रुप के मैंने सेंटर भी बताया था। Center of G is identity and A square। इस तरीके से था ना। If G is equals to Dn, n is greater than equal to 3, then center of Dn is equals to identity when n is odd and identity comma वहाँ पे x की पावर n/2। x वहाँ पे आपका क्या डिनोट कर रहा था? रोटेशन। x is rotation, then n is even. Here n is 4, so identity and x to the power 4/2, x square हो गया ना, तो a square यहाँ पे रोटेशन a डिनोट कर रहा है। ठीक है। सो फर्स्टली सबसे पहले तो ऐसे ही देख लो ना, G/ZG इज आइसोमॉर्फिक टू विच ग्रुप। जिसके भी आइसोमॉर्फिक होगा ऑर्डर शुड बी सेम। सो ऑर्डर ऑफ G/ZG,
जी का तो फिर 8 हो गया।
यस, 8
और
by
ZG का 2 है।
4
हो गया।
A part is discarded, ट्रिवियल ग्रुप का ऑर्डर 4 तो होता नहीं। C2 दिस इज ऑल्सो डिस्कार्डेड, V part। ठीक है। Now G/ZG has no element of order 4. So this implies that G/ZG cannot be cyclic. So if it cannot be cyclic, then option D is also discarded. Therefore G/ZG is isomorphic to C2 cross C2, because C2 cross C2 is not cyclic, because we know that Zm cross Zn is cyclic if and only if GCD of M and N is 1. Here it is not 1 na? So it is not cyclic. एक और वे से भी कर सकते हैं, वो वाला भी बता देती हूँ। So G/ZG has order 4, so it can be either isomorphic to Z4 or it can be isomorphic to C2 cross C2, because both has order 4. Now if G/ZG is isomorphic to Z4, as Z4 is cyclic?
So it can't be possible because it is not cyclic.
Z4 is cyclic implies abelian. Z4 is cyclic implies abelian also, because every cyclic group is abelian. So if Z4 is abelian, then it is isomorphic to G by Zg. So G by Zg should be abelian. If G by Zg is abelian, this means that G is abelian, because this means that G is equals to Zg, na? This means G is abelian, which is a contradiction because dihedral group is non-abelian. Therefore, G by Zg is isomorphic to C2 cross C2. Next, fundamental theorem of finite abelian groups. Every finite abelian group can be written as a direct product of cyclic groups of prime power order. Means if G is a finite abelian group, then G is isomorphic to Z P1 to the power N1 direct product, Z P2 to the power N2, so on till Z Pk to the power Nk. Writing a group in this form is called determining the isomorphism class of G. Note, there is one group of order P to the power K for each set of positive integers whose sum is K, means partitions of K, written as so on till Zpk to the power K Nk, where K is equals to N1 plus N2 so on till Nk. This is now order of group G partition of K. Basically, I need to partition this power. Possible group. So, order of G, P. Its power is 1. Partition of 1 is 1 only. So, possible group is ZP. Next, P square. So, partition of 2 is 2 itself and 1 plus 1. So, ZP square and ZP direct sum ZP. ऐसे ही कर रहे हैं ना, ZP1 to the power N1 direct sum ZP2 to the power N2 and so on. If it is P cube, then 3, 2 plus 1, 1 plus 1 plus 1. This is ZP cube, ZP square direct sum ZP, ZP direct sum ZP, direct sum ZP. P to the power 4. Partitions of 4 will be 4, 2 plus 2, 3 plus 1, 2 plus 1 plus 1 and 1 plus 1 plus 1 plus 1. Z P to the power 4, ZP square direct sum ZP square, ZP cube direct sum ZP, ZP square direct sum ZP, direct sum ZP, 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 ZP. Note: to find the number of non-isomorphic abelian groups of order n, first step is prime factorize n. P1 to the power k1, P2 to the power k2, so on till Pm to the power km. Second step, the number of non-isomorphic abelian groups is given by the product Pk1, Pk2, so on till Pkm, where this Pk1 denotes the partition of K1, Pk2 denotes the partition of K2 and so on, where Pki denotes the partition of Ki. I lies between 1 and m. For example, find the number of non-isomorphic groups of order 100. So firstly, prime factorize is 100. So 100 can be written as 2 square into 5 square. Then I need to partition this powers. Partition of 2 is 2 na. Therefore, number of abelian groups of order 100 is equals to partition of 2 into partition of 2, which is 2 into 2, 4. Find the number of non-isomorphic non-abelian groups of order 8, 6, 20, 360, 15. Next question. Up to isomorphism. The number of abelian groups of order 108 is 12, 9, 6, 5.
Up to isomorphism means non-isomorphic. अच्छा. 6 है इसका आंसर.
सेकंड वाले क्वेश्चन का
सेकंड वाले का
काला नहीं, मैंने देख लेती हूँ एक मिनट. 108. So 108 is equals to 2 square into 3 cube. So partition of 2 is 2, partition of 3 is 3. Yes, 6 answer. Number of abelian groups of order 108 up to isomorphism is equals to partition of 2 into partition of 3. 2 into 3, 6. ये वाला हुआ.
इन सबका तो अलग अलग निकालना है ना.
अलग अलग.
तो ये फर्स्ट 8 वाले का आंसर आएगा 5. नॉन आइसोमॉर्फिक नॉन अबेलियन है ना ये, तो इसमें अबेलियन 3 होंगे, तो 8 में से 3 के 5 नॉन अबेलियन हुए ना, ऐसे पता है
क्या?
ये है फाइंड द नंबर ऑफ नॉन आइसोमॉर्फिक नॉन अबेलियन।
नहीं, एबिलियन ही था, गलती से नॉन एबिलियन लिख दिया। एट की प्राइम फैक्टराइजेशन
3 आएगा, फिर तो 2 का क्यूब हो गया ना, 3 आएगा, फर्स्ट का 3,
यस, दिस इज,
और सेकंड का 2, और सेकंड का 1, सॉरी
2 into 3, yes 1,
1 हुआ, इसका हो गया 2 एंड 5 की कितनी होंगी?
2 स्क्वायर इंटू 5 की पावर 1 ना।
हाँ अच्छा, 2 into 1, 2 ही हो गया फिर तो, ठीक है। स्क्वायर 3 2 का क्यूब, 3 स्क्वायर एंड 5 1, तो 3 into 2 6, 360 की 6 हो गई,
2 क्यूब इंटू 3
एंड
स्क्वायर
15 का 1 हो गया।
partition of 3 3 into partition of 2 into 1 6.
इसका 1 आएगा, 1 into 1 1।
The number of non-isomorphic abelian groups of order 24 is
3
yes 24 is equals to 2 cube into 3, so partition of 3 into partition of 1 3. This question was from June 2015. Next, consider the set of matrices G is equals to S B 0 1, B belongs to integers, S belongs to minus 1 comma 1, then which of the following is true? A part, G forms a group under addition. B part, G forms an abelian group under multiplication. C part, every element in G is diagonalizable over complex. D part, G is finitely generated group under multiplication.
सी ऑप्शन एक तो करेक्ट आ रहा है इसमें, इसलिए
पक्का?
क्योंकि एवरी टाइम इसमें डायगोनोलॉजिकल मैथमेटिक्स तो बनी रही है, कोई भी अगर एस की वैल्यू लूं, बी की कोई भी वैल्यू लूं,
If I take B as 1 and S as 1,
हाँ, then also it is diagonalizable, no?
1 1 0 1. So its eigenvalues are
1 1.
1 1. So AM is 2 and
अच्छा,
what is G?
yes, sorry.
GM of
डायगोनलाइजिबिलिटी चेक नहीं करी मैंने, राइट, मैं सिर्फ डायगोनल एंट्रीज को देखती हूँ।
नहीं, ऐसे नहीं.
हाँ, ठीक है,
2 minus rank of A
तो डी
minus.
ऑप्शन करेक्ट होगा फिर इसका, बाकी एबीसी तो फिर रॉन्ग हो गया, डी करेक्ट है फिर इसका।
C is wrong. For A part,
ए पार्ट तो एडिटिव आइडेंटिटी डज नॉट एग्जिस्ट।
या क्लोजर भी देख सकते हैं, 1 B 0 1. If I take S as 1 and if I take S as minus 1, then minus 1 0 B 1 for B belongs to integers. So if I add these two matrices for closure property 1 0 B 1 plus minus 1 0 B1, then it is 0
0.
2 B2. Clearly it does not belongs to G.
क्लोजर प्रॉपर्टी भी नहीं आ रही.
Closure property fails.
तो ग्रुप ही नहीं है तो अबेलियन ग्रुप ही नहीं होगा ना. अच्छा, अंडर मल्टीप्लिकेशन भी नहीं आएगी ये.
सो ऑप्शन बी के लिए भी सिमिलर मैनर में 1 0 B1, this belongs to G. And minus 1 0 C1, this belongs to G. Commutative property will not hold here.
Fails.
This is not equal to minus 1 0 C1 1 0 B1. So G is not commutative. So option B is also wrong. So A, B, C are discarded. So D part is correct. G is finitely generated group under multiplication. Okay. Next. Normal subgroups and factor groups, means quotient groups. So definition of normal subgroups. Let G be a group and H be a subgroup of G H is said to be a normal subgroup of G if every left coset of H and G is equal to some right coset of H in G. That is, AH is equals to HA for all A belongs to G. It is denoted by H is a normal subgroup of G. Here, normality condition does not mean abelian. That is, if AH is equals to HA, this does not imply that AH equal to HA for A belongs to G and H belongs to capital H. This means that if A belongs to G and H is an element of subgroup G, then there exists H dash belongs to capital H such that AH is equals to H dash A. Next, what is a normal subgroup test? Let G be a group a subgroup H of G is normal in G if and only if XH X inverse is contained in H. Or we can also say that X inverse belongs to H for all X belongs to G, for all H belongs to H. Next is proper normal subgroup. Let H be a proper normal subgroup of G. It is said to be a proper normal subgroup if there exists G belongs to group G such that G does not belongs to H. Means G is an element of group G but it is not an element of subgroup H. Next, trivial normal subgroups. Identity and group G itself are called trivial normal subgroups of a group G. Next, examples. First, every subgroup of an abelian group is normal. Means if group G is abelian, H is a subgroup of G, then H is normal. That is, H is a normal subgroup of G. Second, the center of any group G is normal in G. The center of any group G is normal in G. That is, center of G is normal subgroup in G. Third, let G is equals to GL to R. मतलब general linear group of 2 cross 2 matrices having real entries. A belongs to M2 R such that determinant of A is non-zero, and let H is equals to SL2R, and I need to show that this special linear group is a normal subgroup of general linear group. This is equal to A belongs to M2R such that determinant of A is 1. यहाँ A की जगह B ले लेते हैं. Then SL2R is a normal subgroup of GL2R. Let A belongs to G and B belongs to H. Consider determinant of A be A inverse. This is equal to determinant of A into determinant of B into determinant of A inverse. Determinant of A is 1. Sorry, determinant of B is 1. Determinant of A into determinant of A inverse. This is determinant of A into A inverse. So this is 1. So clearly AB inverse belongs to H for all A belongs to G, comma B belongs to H. So SL2R is a normal subgroup of GL2R. Let G be the group of all invertible 2 cross 2 upper triangular matrices under matrix multiplication pick out the normal subgroups of G from the following. A part, H is equals to A belongs to G such that A12 is equals to 0. B part, H is equals to A belongs to G such that A11 is equals to 1. H is equals to A belongs to G such that A11 is equals to A22. Try this. This is MSQ. More than one option can be correct.
फर्स्ट टू तो है, ए भी आ रहा है, बी भी आ रहा है, थर्ड में चेक करती हूँ।
ए नहीं आएगा, ए पार्ट रॉन्ग है।
0 0 अगर हम, अच्छा अगर पर्टिकुलर केस हम बी को भी 0 ले लें डायगोनल एंट्री में तो फिर वो 0 हो जाए, तो हम कह सकते हैं अदरवाइज। पर यहाँ पे तो ये है ना, इन्वर्टिबल है ना, तो अगर इन्वर्टिबल है और अपर ट्रायंगुलर मैट्रिक्स है तो नन ऑफ द डायगोनल एंट्रीज कैन बी 0। अच्छा A12 तो 0, पर A12 का 0 हो भी गया तो उससे फर्क करना पड़ रहा है। इन्वर्टिबल तो तब भी रहेगी।
If I take B matrix as 1 0 0 2, A matrix as 2 1 0 3, it is clearly upper triangular. Its entry A12 is also 0 and it is invertible also. Determinant is non-zero.
तो अगर A B इनवर्स निकालेंगे इसका फिर
A B in A inverse. So A inverse will be 1 by 6
3 2
0 1
plus
A 1 1 1 2 1.
-1 आएगा ना।
1 by 2 0 minus 1 by 6 जो ट्रांसपोज करना है, minus 1 by 6 0 1 by 3. Now A B A inverse 2 0 1 3 1 0 0 2 A inverse 1 by 2 0 minus 1 by 6 1 by 3. So 2 2 0 6 1 by 2 0 minus 1 by 6 1 by 3. So this is 1 0 1 by 3 2. This belongs to G, this belongs to H. Now here A12 entry is non-zero na, it is not equal to 0. So this does not belong to H.
H से belong करता है।
So H is not a normal subgroup of G. Check for B and D also. B and C.
B तो फिर आ ही रही है, B तो हो रहा है, और C वाला चेक करती हूँ। तो इसमें डायगोनल एंट्रीज दोनों 1 नहीं आएंगी।
एक सेकंड रुकना, मैं 1 मिनट में आएगा। हाँ आप बोलो क्या कह रहे थे आप?
दोनों डायगोनल एंट्री सेम नहीं आएंगी ना इस केस में?
दोनों डायगोनल एंट्रीज
P पार्ट्स में A11 और A22 दोनों सेम नहीं आएंगे।
B part H is equals to A belongs to G such that A11 is equals to 1. So if I take matrix P as 1A 0 B, matrix Q as C0 D E, where P belongs to H and Q belongs to G, and Q inverse will be 1 upon determinant of Q C E minus D 0 C. So QP Q inverse, Q is C0 D E, P is (1 0) AB Q inverse 1 upon C E 0 minus D C. So this is equal to C0 CA plus BD BE 1 upon C0 minus D upon CE 1 upon E. Finally this is 1 AC plus BD minus D upon E 0 B. Now as A11 of QPQ inverse is 1, this means that QPQ inverse belongs to H.
I'm saying the third part, ये तो आ रहा है, ये तो हो रहा है second वाला, third वाला,
C part is
A11 equal to A12.
H is equals to A belongs to G such that A11 is equals to A22. Diagonal entries are same. So simply take matrix M as A B 0A, this belongs to H, and matrix N as C D 0E. थर्ड पार्ट क्या कह रहे थे, आएगा नहीं आएगा?
सेम नहीं आ रही मुझे,
नहीं आ रही. M N sorry N M M N M N inverse C0 D E A0 B A 1 by C 0 minus D by CE 1 by E. So this is equal to CA CB plus AD 0.
यहाँ पे 1 by C आएगा ना, C upon CE हुआ ना इसका डिटर्मिनेंट. अच्छा हमने उल्टा किया, ठीक है ठीक है, got it.
CB plus AD EA, and this is 1 by C 0 minus D by C 1 by E. This is equal to A0 CD by E, and this is A. Now as A11 is equals to A22 in NM N inverse, so it belongs to H. So H is a normal subgroup of G.
मैं चेक कर लूँगी मैंने कहीं मिस्टेक करी होगी.
So answer is option B and C. ठीक है, इसके बाद से कल कंटिन्यू करते हैं. ठीक है,
ओके.